design intelligence grows exponentially, and at some, so it goes to infinity, and it becomes a super AI. It can, so essentially they say that whoever achieves singularity, achieves super AI, will advance in technology. In 6 months, will advance more than what we could advance in 100,000 years. For example, if Russia achieves singularity, Russia's army achieves singularity, so they become so advanced, so technologically advanced, so quickly that they dominate the world forever. They become the superpower of the world forever, and there is no way to take them down. So we will be their slaves. So you want questions?
Yeah, also in that, so once it does reach singularity and it's smarter than humans, will it decide making type decisions?
We decide what?
It will make its own decisions.
Oh, make decisions by itself.
Yeah.
So whoever makes it decides what it can do. So it is powerful. It makes its own powerful. It is a powerful tool. At the end of the day, it is a tool. So it is a powerful tool for its own. So whoever owns it, it's like having a nuclear bomb, having a super nuclear bomb. It's very, very powerful. So it must. So we don't know what kind of technologies it can achieve, what kind of weapons it can create. But it's so it is a super AI. So just think of infinite intelligence and what kind of weapons it can create. So definitely the owner of this intelligence, this super intelligence, can dominate the world, can overcome almost any obstacle. So it is really dangerous. And so that's why some people predict that the world, so there are two different predictions. Some people predict that the world will move towards more democracy, so the world will become more and more democratic because the countries are becoming democratic one after another. But with the super AI, it is predicted that the world becomes one dictatorship and stays in dictatorship forever. So whoever achieves the singularity will become the dictator forever, the dictator of the world forever. And so that's why it is dangerous. So do you think we should have laws to control AI? But Russia doesn't have any laws to control AI. So if we control AI here in the US, they are gonna surpass us and they're gonna just achieve singularity sooner than us. So who thinks that we should not have laws to limit AI? That's my opinion.
Someone could get super AI and they're just going to create that.
So I hope that the United States gets there rather than Putin. So if anybody achieves super AI, I prefer a democratic country achieves super AI. So not Russia or China or North Korea, or God forbid. So if they achieve AIs, achieve super AI, we are doomed. Seems that you disagree with me.
I just think people are still really bad at using computers. We undervalue that, I think, in terms of when we're going to reach the super AI, that we're just this bad at valuing computers.
So
like, even if Putin had a supreme AI, I don't know that he'd know how to use it well enough. Like, he'd need a team of other people to use it, unless it's wholly autonomous. And in that case, I don't know why it would continue to work for him. We'd probably get rid of him first. He would be his first barrier to, Putin would be its first barrier to doing something else, whatever it wanted.
I see.
If it started
So
there.
I am sure he has teams of top engineers.
You smile and nod and
Yeah,
don't get shot.
who obey him.
Yeah.
Okay. So the next thing that I wanted to mention is that there is a debate about AI replacing humans doing jobs and taking their jobs. So what do you think? Do you think AI will take our jobs? Really? So we have a labor crisis, kind of unemployment crisis. So what do you think? So what is your major? MIS. Okay. So yeah, AI can do some stuff that you do. So, for example, programming. Now you can tell ChatGPT to write a code for you. So you give it a problem and it writes the code for you. And it writes very clean code. So it can code in almost every language. I tried Python, JavaScript. I didn't try R, but I'm sure it can do R. And I tried C. It can code in C. So it can code in many languages. I tested a couple of its code. They're perfect, and no exception. So again, there was a tricky mathematical problem. So it could just write a code that considered all possible, all exceptional points. So you couldn't make it to give an error. You couldn't break it. So I think AI is replacing programmers very soon. What's your major? Entrepreneurship. Okay. Entrepreneurship involves knowing the law and creating, so having ideas, ideation. AI can do that too. So ideation and being creative. So you may think that, okay, AI can only combine things and cannot create a new thing, cannot innovate, but actually that's what humans do too. So humans also combine things to innovate. So we learn from the nature, from different areas, and adjust them, combine them just to make new things, to be creative, to innovate. So innovation is something that AI can do too. And entrepreneurship, definitely AI can do that. So I'm sorry, but I think AI can do almost everything in the near future. Almost every job that humans are doing now in the near future. So what do you do? What's your major? Law and economics? Oh, that's interesting. So, we have actually AI lawyers. So there is a software that actually ChatGPT can give you legal advice.
Well, legally, it cannot give you legal advice.
It says that
Yeah.
you should not count on my legal advice. It says that, but it actually gives you.
My lawyer says the same thing. What's the difference? Anyway.
Yeah, exactly. The lawyers also say the same thing.
Can I file your taxes? I want to know if I can use TurboTax. Hmm.
But I think that AI maybe can manage basic, like your
But yeah, so AI can help you to file your taxes. But if you want to optimize your taxes, you want to avoid to pay taxes, you want to minimize the amount of taxes that you are paying. So you should have strategies. You should have strategies to, you know, consider the different deductions, things like that, and have to spend out of your, you know, company's bank account, and be careful how you spend it, you know. So you should spend your money through businesses, etc., etc. And these strategies also can be created by AI. So AI can also find good strategies. I think. So, in my opinion, someday AI will be able to do every job better than humans. But
I think you have to
I'm too optimistic.
maybe
So yeah. So whatever it can do, it can replace every job except the teachers. So, but I think no, of course it can replace teachers. It can replace researchers too. And it's interesting that if you a couple of years ago there was a patent that was there was a patent application that was submitted to the was filed into USPTO. And one of the inventors was an AI. So the AI was participating in the innovation and creation of the patent. And I think this also happened in China. Good. So, yeah, any other question? Any comment? So now let's talk about clustering. We are done with AI. I just wanted to let you know what AI is. The topics that I covered are related to a category of AI called NLP. So NLP is something that we don't cover in this course, but it's important. ChatGPT, Turing test, singularity, all of these are related to NLP, natural language processing. We don't cover that here, but maybe someday you will have to learn it. So today we talk about clustering. Clustering is a type of unsupervised learning. We talked about supervised and unsupervised learning on Monday. Clustering, what we do is that we try to group the data points into clusters just automatically based on an algorithm or something. For example, we have people with different sizes, you know, different sizes in terms of waist size, chest size, you know, height, things like that. And let's say we have like the sizes of 1,000 people. So everybody is different. We cannot just produce 1,000 different t-shirts. So customize every t-shirt for every person. We cannot just produce or manufacture just one t-shirt and say, okay, all of you just one size fits all. No, it's going to be too small for some people. It's going to be too big for some others. It's not a good solution. What we can do is that we can have like 4 sizes: small, medium, large, extra large. And then just these 4 sizes would cover almost everybody, and almost everybody would be comfortable with one size. You know, anybody would be comfortable with one size. Now, this is the question: what sizes should be these four sizes for t-shirts, for sizes of t-shirts? That's a very important question. So that's clustering. In fact, we want to have 4 clusters of people. We want to put people in 4 clusters. And then the centroids of these clusters would be the sizes of the t-shirts. Okay. Another example would be the libraries. In the libraries, we should classify the books. Somehow we should put the books in different categories, and we should put the books somewhere in the library. And how would you cluster the books or classify the books? You should decide about the topics, about the subtopics, things like that. So we can have, so what we should do is that we should just compare the texts of the books and see how similar they are. And the ones that are more similar to each other should be more likely to be in one category, and the ones that are dissimilar to each other should be in different categories. And after clustering, we come up with like 12 different clusters of books. And then we look at each cluster and see what type of books are in this cluster. So we see one cluster and we see, oh, it's fiction. We see another cluster and see, oh, it's math. The other cluster we see, oh, it's law. Another cluster, it's economics. Another cluster is science. So then we label them. The computer cannot label them. The computer can just put them into different clusters. Then we decide what label to put on each cluster. So keep this in mind always. The computer just gives us cluster 1, 2, 3, 4, 5, 6. That's it. So it just gives us the clusters. Labeling will be up to us. That's the difference between classification and clustering. That's one of the differences between classification and clustering. Today, we are going to talk about one powerful method for clustering, K-means. K-means is a very powerful method for clustering, maybe the most powerful method because no other method has proven to be better than K-means in clustering. And it is used widely in business. So we have data points. What we do is that when we use K-means technique, we have K clusters. And of course, each cluster has a centroid, which we call mean. So the mean of each cluster would be the centroid of the cluster. So that's hence the name K-means. There are K-means, K-centroids. And it is a very simple and powerful technique. And it's very good for this course. Especially in this course, you should learn an unsupervised learning method too. And this is a very good unsupervised learning method. So how does it work? The first step is that we give it the number of clusters. We say like we want 4 clusters. We have to specify the number of clusters for K-means. Okay. We first specify the number of clusters. Then we generate K random points in the space, or we can just pick K random observations in the space. So we have observations, we just pick K of them randomly, and we call them centroids. So the first set of centroids that we have are just randomly selected. Then we are gonna see for each point, for each data point, we are gonna see which centroid is closest to that data point. That data point will belong to that centroid, will belong to that cluster. Therefore, we have clusters, right? So we're done, right? You have just k clusters. We're done, right? No, we are not. These clusters are not optimal. We want optimal clusters. Optimization is important. So what we do in the next step is that we find the mean for each cluster based on the data points that are in that cluster. We find the mean for each cluster. The mean will be, most likely, the mean will be different from the centroid. So now what we do is that we move the centroid towards the mean. We move the centroid to the mean. So the means become the new centroids. Okay? Now what we do is that the new centroids, for the new centroids, we just cluster again with the new centroids. We see for each point, we are going to see to which centroid new, to which new centroid the data point is closest, and then the data point will belong to that cluster, which can be different from the previous cluster. Okay, so the data points can change clusters. After we do that, we have new clusters. Then we recalculate the means. We have new means. Then we move the centroids to the new means. We have new centroids. Then we form the new clusters with the data points. And again, and again, and again, until the point that it becomes stable. It converges into one arrangement of cluster. So let's look at this example. You have these data points. It's very simple example. It's a very simple example. And we want two clusters. We want to cluster these data points into two clusters. What is the first step? We should just pick 2 points, 2 random points as centroids. Just pick 2 random points as the centroids. And what's the next step? We should do the clustering. When we have the centroids, we do the clustering. We cluster the data points into the 2 clusters based on to which centroid they are closer. So the data points are clustered based on, are assigned to each cluster based on to which centroid they are closest. So the result will be something like this, of course. These data points, the blue data points are closer to the blue centroid, and the red data points are closer to the red centroid. So far, so good. Now, we are gonna calculate the means for the 2 clusters. So the mean for the blue data points will be somewhere here. And the mean for the red data points will be somewhere here. So we have the means. That means we have the new centroids. The centroids are moved to the new means. And then we are going to reassign the data points to the new clusters. Reassign the data points to the new clusters. See? We reassign the data points to the new clusters like this. And then what happens is that so what happens? What is the next step at this point? Go ahead.
Go back to step 4.
It's what?
Go back to step 4.
Go back to step 4? No. At this point, we have to recalculate the means again, because the data points have changed clusters. So we have to recalculate the means. We will have new means. The centroids will move to the new means. We will have new clusters, right? The data points will change clusters. And it is proven that this k-means method will always converge. So it will eventually become stable. Okay. So we know that at some point it will converge, and no data point will switch clusters, which means that the mean will stay the centroid, and the centroid will be the mean, whatever. So here is an example, a very interesting example that can show you what happens in clustering. It is something natural k-means, natural k-means that will happen in life, that could happen in life. So let's imagine we have buildings, residential buildings or houses in an area, like in a rural area, we have houses arranged like this. And we have 3 kiosks of food, like kebab kiosks. And we have 3 kiosks that can move. At first, these kiosks will locate at random locations in the area, right? Then what happens is that each house, the residents of each house will go to the kiosk that is nearest to them. They will go to the nearest kiosk to get kebab, right? So we have the green houses here, the red ones here, the blue ones here. Essentially, we have 3 clusters. The ones that are closest to the green one will go to the green one. The ones that are closest to the red one will go to the red one. The ones that are closest to the blue one. So each house will decide which kiosk is closest to them. So that house will go to that kiosk. Essentially, it partitioned the houses into 3 clusters. Then what happens is that each kiosk will think, okay, now I know my customers. Where should I be? Where should I locate myself? I should be at the center of the customers. So each kiosk knows its customers. So it will go to the mean of the locations of the houses. That means the centroid, the center of the houses. So essentially, the kiosk will move to the centroid of the houses. Each kiosk will go to the centroid of the houses, and the kiosks will have new locations. After the kiosks move, the distances between the kiosks and the houses will change. Therefore, some houses find the other kiosk closer to them and will change their, their provider. So, and we use another kiosk for kebab. So we have a new arrangement here, a new partitioning here, based on the new locations of the kiosks. So what will happen is that now the kiosks have new customers. And they again think that, okay, they should be at the center of their customers. Again, they move. And after they move, the customers change. And then they want to be the center of the customers. And then they move. And then the customers change. So it happens millions of times, not millions of times, just a few times. And then eventually we are going to reach a stable point at which each kiosk is the centroid of a bunch of houses, and also the mean of those houses. The mean, I mean the center of gravity for those houses. Okay, the centroid and the center of gravity. So it doesn't have any incentive to change location. That's what K-means is. Is it clear? So the algorithm for K-means is this, and it's a very powerful clustering algorithm. So the advantages of K-means are that, first of all, it is very simple to implement. It's a very simple algorithm. You can write the code, but R actually has the code for you. And it can scale to very large data sets. You can have millions of data points, and it can just cluster them very quickly. guarantees convergence, we always converge to stable clusters. Easily adapts to new examples. Of course, you can use it on different clustering problems. And of course, it generalizes to clusters of different shapes and sizes. So the size and shape of the cluster doesn't matter. The cluster can have different shapes. The proximity of the data points to the centroids matter. There are some disadvantages too. The user needs to specify K, so you have to decide how many clusters you should have. But there are actually methods to help you with that. I'm going to talk about those methods. Being dependent on initial centroids, yes, that is actually a problem, but there are actually methods to fix that. So, you know, it depends. Sometimes the final solution is different when you start from different points, different random points. So remember, the initial centroids are randomly selected. So if you start like this, you may end up with a different solution than if you start like this, you know? So where you start can affect where you end. That's actually a serious problem sometimes. And another problem is that centroids can be dragged by outliers. So we know about the outliers. The centroids can be moved away by outliers. For example, here you can see that we have one outlier here. The centroid goes here, and therefore, when we cluster, we have these 2 dots in this cluster, and we have like 2 clusters. These 3 dots are in this cluster, the other dots are in this cluster. So it doesn't make sense because the clusters should be like this. The centroid should not be moved to the outlier. So how can we fix that? It's super easy. Just have one more cluster, or just a few more clusters. Consider having, instead of 2 clusters, consider having 3 clusters. When you do that, the outlier will fall in the cluster by itself, and so it will not drag the centroid from the other clusters. That's actually a powerful method to do that. Of course, we have other methods for outliers to can trim the outliers, just remove the outliers from the model. Windsorize, can windsorize the outliers, right? And of course, you can have additional clusters for that. So the outliers problem can be solved easily. What about the initial centroids? So let's say we start, so we have these data points. Let's say we start with these 2 centroids. The centroids are up and down like here. We will end up with these 2 clusters. However, if the centroids are left and right, we will end up with these 2 clusters. So the end result will depend on where we start. Okay, how can we fix this? Yeah. So what we can do is that we can start from different starting points and run the clustering multiple times. So one random point and run it, another random point and run it, run. And we run the clustering, we run the K-means algorithm like 10 times and see if we end up with different results at the end, with different solutions. If we end up with the same solution all the 10 times, okay, there is no problem there. But if we end up with different solutions, we are going to compare the solutions in terms of the efficiency of the outcome, which is actually WSS. So we're going to talk about WSS. and that's the weighted square distances within square distances with the clusters. So, and then we pick the one that results in the lowest square distances. So within clusters, the square distances should be the smallest. The clustering result, the clustering approach that results in the smallest distances within clusters will be the best one. Okay, so we are going to talk about it in a bit. Don't worry about it. What was the other problem? The other challenge? How many clusters? That's actually a very important challenge. To decide how many clusters, we are going to use the elbow method. Again, we are going to run the algorithm several times with several numbers, and then we are going to decide which number of clusters is the best. So to discuss that, let's first understand what is distortion. Distortion, you don't need to memorize these formulas, but just try to understand. Distortion is about the distances within each cluster. So in each cluster, the centroid, let's say the centroid is actually, we are talking about the final solution. When we run the algorithm at the end, in the final solution, the centroid would be the mean, right? Mu is the centroid. Mu is mean and is the centroid. So the centroid, the distances, the square distances between the centroid and all the data points within that cluster would be W of that cluster, okay? Or distortion for that cluster. The distortion for that cluster would be that. So we have W of each cluster like this, the distances between the centroid and all the points that belong to that cluster, that are within that cluster. So that's it. Now, when we sum up all these W's across the clusters, like let's say we have 5 clusters, we sum up all the W's across all these clusters, we get WSS. The within cluster sum of the squares. Within cluster sum of the squares. And that's actually sum of distances. Okay. So let me show you how it looks like. So let's say we end up with this centroid and these clusters and these data points. This other centroid, and this is another centroid. We have this cluster. This is the final solution after running the algorithm. The W of CK, that W of C1 is this. With distances, we add them up, sum of the square distances for this one. So C1 is sum of the distances, all distances. Then C2 is sum of the distances for this one. C2, sum of the J. And then C3 or sum of the other. So sum of the distances within each cluster. And then we sum them up. So WSS is actually sum C, or C1 plus C2 plus C2. And we sum W. So WSS is sum of W. WSS is sum of W. That's it. And it's W1 for W of C1 plus W of C2 plus W of C3 plus W of C3. And that is the weighted within classes of the squares. That's a very important metric. Another metric that we have is between clusters of the squares, which is actually the distance between the clusters, so distances across clusters, but don't worry about that. You don't need to learn that. So just focus on WSS. So what we have here is a very good measure of the optimality of the result. What we can do is that we can have this diagram based on WSS for different number of clusters. When we increase K, what happens is that WSS decreases. Why? Why WSS increases? Decreases. Why does WSS decrease when we increase K? Because when we have more centroids, the data points can find closer centroids, right? So each cluster will be smaller. When we have more centroids, each cluster will be smaller. That's simple. And what happens is that when we have just one cluster, it's the maximum. WSS is maximum when you have just one cluster, because it's just the mean of all the data set. The centroid is the mean of all the data set, and it is a very large number. But when we have two clusters, so we have two centroids, so we are partitioning the data set into two, so it becomes better, it is more efficient. And then we have 3, and then 4, 5, 6. So the number of clusters increases, the WSS decreases. That's for sure. However, at some point, the decrease in WSS is not enough. So WSS does not decrease that much. We are increasing the number of clusters by 1, but WSS is not decreasing that much after 3, you see? So it is like flat after that. After 3, it is flat here. But before that, we see sharp decline, sharp drop in WSS. So definitely 3 is better than 2. But it's 4 better than 3? Slightly better. Probably not worth it. We don't want to have too many clusters. So the point at which we have this break, this sharp change in the slope. When we have this sharp change in the slope, that means what? That means we have the optimal number of clusters. So here, we call it the elbow point, because at this point, the slope changes. Instead of decreasing sharply, it decreases. So before that, it decreases sharply. After that, it decreases very smoothly. Okay. So we have a very so we have an angle here. It's the elbow point. The change in the slope, the maximum change in the slope of the changes. You know. Let's look at an example. Here we have one cluster, just one centroid, but one cluster. This is the maximum WSS. We have 2 clusters, 2 centroids. The WSS drops significantly because the data points are very close to this one, and they're close to this. But when we have 3 clusters, the WSS drops a lot, significantly again. WSS drops significantly. And like, essentially, we are here first, and then we are here, and then we are here at the point at which it is the WSS is small enough. But if I add another data point, I mean another centroid, another cluster, if I have 4 clusters, it is not gonna drop significantly, as you can see, because the fourth cluster, the fourth centroid, it will be close to one of these, right? That means the 3 centroids would be the best. 3 centroids, the 3 clusters would be the best. Remember the elbow rule. Elbow rule is for deciding the number of clusters. So we fixed, so we could handle the number of clusters just systematically using this. We can also deal with the outliers, right? And actually, this can help with dealing with the outliers, because automatically when we have outliers, the WSS and the elbow method will give us one additional cluster, because we will need one additional cluster to minimize WSS, you know, to get a good deal of WSS. And what was the next one? What was the other thing that we were concerned? Oh, about the initial conditions, starting point. So when we have, when we reach different solutions with different starting points, which solution is the best? Which starting point is the best? WSS. We just decide based on WSS. Whichever results in the minimum distortion is the best starting point and the best solution, right? So that problem is also solved. So remember this here, yeah, this case. So between these two, we should select one. We have 2 clusters, 2 clustering solutions. Which one is the best? WSS. And my guess is that the second one has a lower WSS. And that means the second one is a better solution than the first one. Okay. The question. We are done. We are done with clustering. Are we good? Okay. So let's do some examples in R. Do you want to have a break for like 2 minutes? Is there an event or something today? Is there a football game? I'm really surprised. So many students can show up today. They have to learn clustering by themselves. That's their problem. For clustering, we are going to use the dataset scores.csv. Let's change the working directory. For the dataset dimensions, we have 100 data points, 100 students, I think. And student ID, hours, sleep, they slept before the exam or not, the previous grade, and the grade. Let's plot the scores. Okay. Space. We can use pairs or plot to make scatter plots, and we can give the scatter plot multiple variables, multiple lists, and it will just throw each variable against the other variable. You know, each variable against the other variables is actually throwing all variables against each other in this matrix of scatter plots. We have a matrix of scatter plots here. We have hours versus sleep. We have previous grade versus grade. Kind of correlation. I can see kind of correlation here. Now, I'm going to just focus on fourth and fifth columns. That's the grade versus previous. Grade versus previous grade. Yeah. Just see the top 10 for that data. Lot. Now, what I want to do is to scale data, because for clustering, to have the distances. So one problem with clustering is that the distances can be very biased if you have different dimensions. For example, X has a different dimension than Y. Then what happens is that, let's say in this figure, in this picture, that X actually, X has, X is in theirs between here, 10 years and 20 years. Okay. And Y is in sales. For example, 3 million sales to 15 million sales. So, sales. So what happens is that one of your axes has much larger values. So when we want to calculate the distances, we are just thinking delta x2 plus delta y2 as Euclidean distances. We are thinking that's Euclidean distances, right? When we are calculating WSS and W of each cluster, we are talking about Euclidean distances. However, when one of the dimensions is scaled much larger than the other, so that dimension will be the only dimension that matters in clustering. The other dimension doesn't matter. It will be just completely ignored in the clustering, right? The algorithm will completely ignore the other dimension. Because the delta x is like 4 or 5, but delta y is in millions. You know? So delta x will be completely irrelevant. To avoid this, what we do is that we scale the data, scale the dimensions so that all dimensions, all the variables have the same range, have the same variance. So to do that, we use the function scale. Scores data scale. When you scale, you use the function scale. You just scales the variables so that all variables are treated equally. All the variables have the same range. It simply divides them by the variance. That's it. And after that, okay, so now we have the scaled data, the scaled scores. What we should do now is to run the k-means algorithm. First, we need to install a package called Factor Extra. This package actually has the k-means clustering there. I install the package, and then to call the package, to use the package, we should use the library command function, library of that package. And then do the library package. So then one of the commands that we have in this package is fb's lb cluster. So this is just the command that this package has. This is one of the interesting functions. You give the scale data as the first parameter, and then you specify what method you want, the method scale means, and then you specify what algorithm you want, the algorithm scale means, and then the method is WSS. That means you want to minimize WSS. You run this, and it's a very cool plot. Let's run it. Error in graphic. Right, we're going to get back to it later. But for now, let's run the clustering algorithm first. We run km because k means, and we specify the number of centroids, the number of clusters, or k. Centers is the k, and the starting points, it starts from 100 different starting points. It tries 100 different starting points to find the best solution that has the minimum WSS. And the function is called k-means. The result is stored in a variable called km, and in this variable you have these components. You have the clusters, sizes, everything. Iterations within SS, between SS, everything. And within SS is the most important thing, WSS. So KM $sign within SS is this. So it's just for the 3 clusters. We have 3 clusters. So the W for each cluster. And then we can have the cluster scores. So in each score, what clusters we have. We have these clusters. So we have 3 clusters. These scores are in these clusters. You specify the clusters like this. So it puts the data points into clusters and specifies the clusters for the data points. We have cluster 1, 2, 3. And we can just order them if we want. And we can just see them in 3 clusters. The first cluster, the data points in the first cluster are here, and then the second cluster, and then the third cluster. You can see all of them. And Yeah, so if we call it its cluster, it's gonna just make it beautiful plot for us with the clusters that we found. Traffic, there's a problem with traffic. What do you think is causing the problem?
I don't know if it is expecting to exist,
Okay, I can
or if it's because.
loading the correct package right now. So ggplot. So should I just install ggplot as well?
It looks like you already have it installed, because you're getting the warning messages that they were built under different versions of R than the one you're running right now. R updates about every week, or more often. You get warning messages a lot. That might be it. I don't know. Yeah, you're gonna have to restart to.
So thank you.